Thank you for giving an opportunity to make a presentation for our quantum HPC platform activities. So I'm Masahiro Horibe, the Deputy Director of the G-QuAT AIST. So G-QuAT is the Global Research and Development Center for Business by Quantum Technologies. So our activity is not only focused on basic research, but also the business creation using quantum technologies. This slide shows recent situation change and the technology trend of the quantum computing and in the hybrid computing environment. So in the last 5 years, so there is dramatic trend changes, and so shown here. At the 2020s, so it's a little bit users can access the very small size quantum computers in 2020s, but after that, so the many cloud vendors create the cloud access platform to the quantum computers. So the last 2 years, so at the 2023, IBM is released its very large-scale quantum computing chips, and then so QuiLA United States demonstrated to operate the logical qubit. And in the last years, so Google released the new quantum processor Willows, and then so IBM and other computing companies. And so it shows the new concept of the hybrid computing infrastructures. It's CPU, GPU, and QPU systems. And in the business side, so Microsoft and Google, so the other cloud, big cloud vendors collaborate. So small startup companies, atom computing and quantum computing, and so that they try to create the HPC quantum computing platform. And so from this year or from last year's quantum computing area, so try to develop large-scale quantum computers, and in this, so the use cases creations. The trend is completely changed from basic research to business usage development. G-QuAT tried to establish the quantum business ecosystems. So that we set 8 strategic activities and 6 strategic output, and the final goal is the global business ecosystem. Then the first of all, we make many global collaborators to establish the quantum business, including hardware and software, also middleware and any layers. And also linkage with the government strategies, so that we create the platform and testbed to create the industry level use cases and the industry level computing hardware systems. And also the supply chain important to create the realistic hardware, and also the intelligence functions and the IP and the standardization also important to create the business. And the last 2 things is incubation collaborations, and then the competitive environment is also key activities to create business. So this slide shows our key platform for business creations. So first of all, we set up the GPU HPC infrastructures, so-called HPC. This is constructed by 2020 unit of the NVIDIA 100 GPUs. And also, we install the several type of quantum computers, the neutral atom, superconducting type, and then photonic quantum computers. And this platform is open for use for the users. No limit to the project and the collaborations. And the second one is hardware component test bed. And then in Japan, there is many component suppliers, material suppliers to use the huge quantum computer system. So, but they cannot access the test environment because in the case of superconducting quantum computers, they need the cryogenic test bed, but they have no instrument and then no management to operate the cryogenic instruments. So the G-QuAT now establishing this type of component test bed. And last one is the fabrication infrastructures, QFab. So that we can produce the quantum computer chip and then the cryo-electronics devices made of the superconductors. And these three platforms is open for use. We collaborate with the Japanese stakeholders and the international stakeholders, so that we create some products and then create the global quantum industry human workforce. Okay, I'd like to move to the topics of the quantum computers and the HPC computing platform in G-QuAT. So this slide shows the concept of the G-QuAT quantum business ecosystem acceleration strategy. So we are building up the headquarters building, and we will install the ABCIQ GPU HPC. Its performance is 2.1x flops for the AI, and so this HPC platform used for quantum computer researches. And also, other buildings, we will install the Q neutral atom quantum computers, the Fujitsu superconducting quantum computers, and then the other buildings we invite the OptoQC Japanese startups, so they will build up the photonic quantum computers. So all quantum computers are directly connected to the ABCIQ, and so we will establish the quantum HPC hybrid computing platform to provide to end users. So the second floor is also key activities. It's the incubation and collaboration spaces. So we are invite to not only for users, vendors, suppliers, but also the academias and the venture capital and so on. They will stay in this place and then make a collaboration to create the new solutions or new systems or new components, everything. So this slide shows our computing platform strategy for the business ecosystem creation. So the ABCIQ is not only for use as the classical computing resources, but also the gateway to access the all quantum computers. And so the way is set up 3 types of quantum computers, and then also the where we will buy to many types of quantum computers set up in the G-QuAT. So all quantum computers directly connect to the ABCIQ, and then just all users just access the ABCIQ, and then they can access the all quantum computers through the ABCIQ. So also the vendor is staying our site, and then so vendors have so many know-how to use their own quantum computers. So that know-how or the technology transfer or share to the users. The users easy to create the more efficient or more valuable use cases. And then so this is a very good collaboration. And in other words, users access the all quantum computers, and they can compare which performance is best. And this means that so the users accelerate the competition in the vendor side. So this is our one of strategic activities is a collaboration environment and then a competition environment creation. So this slide is a really busy slide. So this slide shows our computing specification in G-QuAT. So previous slide says it shows our computing platform strategies, and so we create the hybrid computing platform. So we need these type of software stacks to easy to access the quantum computer from the users. So we now collaborate with many stakeholders. Also, so we are now installing many types of open source software and middlewares. And then so the ABCIQ is the computing resources, but it is also the test bed to demonstrate the many types of the software and middlewares. So we are happy to collaborate with many software vendor and middleware vendors. Computing platform is the very key infrastructure to create the business, but the most important area is use case creation. And usually quantum computer researcher side try to establish the use cases to use the quantum by using quantum computers. But the existing quantum computers is not large scale, and so not enough computing resources, performances, and then their activity cannot reach the realistic industry problem. So we can now basically collaborate with the existing DX activities. For example, bioinformatics, it's a material informatics, and so. So they have the realistic problem in the industry and the business, and so they already use existing HPCs, and then they try to solve their technical problem or business problem by informatics technologies or data analysis. So the G-QuAT provides the new computing resources to their activities, and So end user side, the access the new computing resources is not only for the hardware but also algorithm and so on. And then after establishing the very large, excellent or also valuable use cases, that achievement will be installed to their business. And then so because each end user research site, they already collaborate with end users. So the end users is the key actor to create the business using the quantum technologies. Okay, next is the next generation quantum computer hardware development. So I'd like to explain the quantum computer roadmap, and so this photograph shows existing superconducting type quantum computers. So the current computers use the very bulky component and then so very big cables and the long cables and so on. And in the next generation, so the IBM already developed shown here, and so very high density cable is used, and then so some of a qubit integrated. But the next 5 years, so the possibly so 1,000 qubit system is created using these type of technologies. But it is difficult to develop so more than 1,000 qubit systems. For example, the 10,000 and 100,000 qubit systems in the one dilutions. So we developed everything. And for example, the cable and the RNA and so on. And also the new technology have to be installed. So this is the two ways. So one activity is the develop the new component exchange from the existing component. For example, now its cable is the coaxial cables, but the future system we have to use the flat cables. And then some of component is now bulky, but we have to use the surface mount type device have to be used. So that we have to miniaturize the component, and then so we have to develop very small power consumption devices. And then the next activity is the cryo-electronics development. And currently, so control circuit and control system is put on the room temperatures. So the very high speed signal, high speed analog signal have to be injected to the dilution. So the cable is so the very large, and then so there is that cable will provide very high heat inflow from room temperature to dilutions. So dilution have to be larger compared to the existing system, and then so there is not power efficiency. So we are now doing the two types of activities. One of them is right hand side. It's supporting the supplier, and then the next is creating the new electronics technologies. And then yes, first of all, we'd like to explain the supplier support activities. So the suppliers have a very excellent manufacturing process and quality control, but they don't have a testing environment. So we support them by the test bed, component test bed, and then so that result can be feedback to design. Parallelly, so we create the international standard to measure the cryogenic component or the high accurate component measurement. It was RF component and optical component, also the material measurements. So this is one of the example to create new component used in the quantum computers. So flat cable, cryo CMOS, and dilution refrigerators, LNAs, the superconducting circuit, and so on. So these type of component basically used in the superconducting type quantum computers and in the silicon spin qubit. Other activity is high pressure photonic devices and the photo detectors and laser controller and so on. So these type of products can be used in the future generation of the neutral atom, trapped ions, and optical and photonic quantum computers. So this slide shows the one example of our test bed activities shown here. So we are now develop the cryogenic workbench to measure the component performance for RF cable or optical cables and other components. So one of the results shown here. So for example, we can measure the transmission loss of the coaxial cables at the room temperatures, from room temperature to the 4K. And also, recently we developed the electron permittivity measurement at several temperatures and several frequencies. So this type of the measurement is required to develop the motherboard and the substrate material development used in the superconducting quantum computers and in the spin qubit systems. Also, this tandem type refrigerator is now installing, and this test bench can be measured the several type of component and several conditions it can be created. So for example, we create the many configuration measurement and the whole amplifiers and some circuit and so on. And the second case is very unique. So usually in the dilution, the cable is connected from the different temperatures. And for example, one side is room temperature 300K, and the other side is 50K. And this test bench can be create that type of condition. One side can be set up 50K, one side is 300K. And so the coaxial cable could be set to between these stages, and one side is 300K, one side is 50K. So this situation is a realistic situation used in the dilutions, and we can collect the measurement data, and then so this data can be used in the whole system simulation, and then so we can design the system level using the measurement result of the test bench. So as an example shown here, left hand side is measured from the millikelvin to the several hundred millikelvin system. Yes, and then so this our dilution is specialized configuration. So basically, the dilution is operation is spent much time, and because the dilution refrigerator is warming up to the temperatures, and then so operator can be open the dilutions, and then change the devices, and then the cooling. So we spend almost 1 week to measure the one setup or one devices. But this configuration is sample holder here, sample holder inserted from bottom side, and then the dilution refrigerator is kept to the low temperatures, so that we can swap the devices very quickly, and then that we can measure so one device less than 1 day. Yes, and the right hand side is the squeeze level evaluation system for the squeezer with the lasers. Oh yes, so we now collaborate with the National Meteorology Institute of Japan in the AIST. So we have so many researchers working in the very accurate measurement areas, and then so this is one of activities to create new evaluation system. Yes. Next activity is developing new technologies. Yes. So the very specific topics is the cryoelectronics, is the cryo-CMOS and the superconducting circuit. Okay. We have some knowledge and achievement for these three types of the cryoelectronics. One of them is cryo-CMOS technologies design, and then the second one is SFQ circuit, and last one is AQFP made of superconductors. And so each cryoelectronics have the different characteristic, unique performance. And then, for example, cryo-CMOS can be made in the existing silicon fabrication fab, and then also it is easy to integrate the many devices and circuits, but the power consumption is quite large, but the superconducting circuit can be create some functions with the very low powers. And then so superconducting circuit have the two different type of circuit. One of them are SFQ, one of them AQFP. AQFP is much lower power consumptions. So we are now already demonstrated. So the AQFP multiplexers to control the qubit shown here, and then we are now developing the new technologies to control the qubit. Yeah, superconducting circuit fabricated in the G-QuAT AIST, as we have the 9 niobium process, also the 11 niobium process. So this photograph shows the cross-sectional view of the digital circuit constructed by 9 niobium wiring layers. So there are the Josephson junctions, so that this technology can be created. So some small scale of the processors, and then so we already demonstrated many types of the processors and so many types of the sensors and so on. Then so we are now improving the process accuracies or so yield and then so upgrade the device performance and so on. So let me summarize my talk. So the G-QuAT is creating the business using HPCs and the quantum computing technologies. And then so our key activities shown here. And it's one of them is use case creation, and the second one is the developing the next generation, future generation quantum computers. So our center is doing two activities parallelly, and so one side is set up the quantum computer. It's provide to end users feedback to the quantum computer hardware side, and the QC side is develop the next generation quantum computers, collaborate with AIST and suppliers and other material vendors and so on. And after developing next generation quantum computers, so that computer is directly connected to the ABCIQ, and the users easy to access the quantum computers quickly, and then they create more large scale or more valuable use cases, and also they find out technical problem, and that problem is feedback to the vendor side. Also, the vendor develop the future generation quantum computers, collaborate AIC and vendors, so tiers. And after that, so this activity to create the industry use cases, also the hardware industries, and so on. And then so this activity is created win-win-win situation for the users, vendors, and then the G-QuAT institute, because the users easy to access many types of the quantum computer or the leading edge quantum computers quickly, and then so vendor side is set up their own machines in the G-QuAT, and they can teach the many users to create the many solutions. And then so vendor side and user side is easy to collaborate to create their own business after that. So that business creation leads to the creating quantum ecosystem. Yeah. So the G-QuAT fully support to many industry stakeholders, its business stakeholders, and to create the quantum computer ecosystem. Thank you for your attention.